Assalamualaikum warahmatullahi wabarakatuh. Today we will present our project for Signal and System Section 1 in Group 4. This is our member Muhammad Ahmed Said, AE240070, Fakrul Adam bin Abdurrahim, CE240132, Ahmad Shaikh bin Azlan, CE240106, Muhammad Imran bin Hamidun, CE240057, and Fatumo Muhammad Abdisilah, AE240068. For introduction, in this project, we study how signal can be analyzed in both time domain and frequency domain. In time domain, we observe how signal change with time, such as waveform shape. In frequency domain, we analyze the harmonic component that make up the signal. To perform this analysis, we use Fourier series, which allow the periodic signal to be represented as a sum of sinusoidal component different frequency. In addition, we apply low pass filter, which is used to remove high frequency component while allowing low frequency component to pass through. This combination helps us understand how signal behave before and after filtering. Next is of our objective. First, to analyze the square wave signal using Fourier series. Second, to study the signal of behavior in both time and frequency domain. Third, to design and analyze low-pass filter based on the given cutoff frequency. Finally, to investigate the effect and duty cycle variant on the harmonic signal and its harmonic content.
A signal is a specification used in our project. For group 4, the signal analyzed a, as a square wave, which fundamental frequency is 250 kilohertz. The low-pass filter is designed with a cutoff frequency of 750 kilohertz, and the initial duty circle is set to 50%. These parameters were used to consistently throughout the MATLAB analysis and circuit simulation. Analysis of a signal in both time and frequency domain. In the time domain, using a more harmonic improvements, the occurrence of a square wave reconstruction, but a small oscillation appear near sharp transitions. In a frequency domain, a signal consists of harmonic components located at integer multiples of a fundamental frequency, which is 250 kilohertz. A small harmonic are included. The frequency spectrum expands with a decreasing amplitude. A Further series is a mathematical technique used to represent a periodic signal as a sum of sinusoidal components. In this project, a square wave is used because it contains a multiple harmonic frequencies. As a number of harmonic increases, the reconstructed wave become closer to an ideal square wave. However, the amplifier of each harmonic decreases as a harmonic order increases.
This part is the fourth series, the manual. The fourth series is used for representing of the periodic signal as sum of the sinusoidal components, as known as harmonic. Each harmonic has a specific amplitude of frequency, and the given parametric is FO is 250 kilohertz of the fundamental periodic is. Then with surge TO 1 over FO, we get 4 microsecond See the duty of cycle of the 50% taking the impulses of the while, then we search T 0.5 TO, we get 2 microsecond. The second step is Fourier coefficient formula. To calculate Fourier coefficient formula, we use the general formula xn 1 over TO multiplying integral of xt exponential power ent what t dt. The integral of the involute of the period signal. Lastly, the second step, solving for the integral, because the signal of n0 only during the impulses, the integration limits are from 0 to t. After integral of the simplifying expression contain of the sine function, which are the showed of the harmonic amplitude on hand. The fourth step, final Fourier of the serial expression. After substitution, all the value the final Fourier series, because summation of the sine term is multiplied by the exponential term. Then lastly, we get the lower harmonic have the higher amplitude, higher harmonic gradual decrease of the multi. This slide shows the MATLAB code using of the general periodic signal using Fourier series with 5, 10, and 20 harmonic. The signal is created by using sinusoidal harmonic using a for loop. As the number of the harmonic increasing, the proximal become accurate. And then we have the time domain of signal 5, 10, and 20. This graph of the shows the time domain signal for the different numbers of harmonic. With the 5 harmonic, the wave is the rough. With the 10 harmonic, the signal can become smoother. With the 20 harmonic, the wave closely match of the original signal. This slide shows the MATLAB code using to analyze the signal of the frequency domain for 5, 10, and 20 harmonic. The formula of the transfer is applied to each time domain signal to obtain its frequency spectrum. And also we have a frequency domain result. This graph shows the frequency spectral for the 5, 10, and 20 harmonic with a few harmonic, only a small numbers of frequency components are present. As the number of the harmonic increases, more frequency components appear and the spectrum become desert.
So this is manual calculation for low pass filter. So when I calculate for FC, which is the formula for FC is 1 over 2 pi RC. So given FC is 750 kilohertz, so omega C equal to 2 pi FC. So put the value to FC, which is 2 pi, and multiply with 750 multiply 10 square root 3, and we get 4.712 times 6 over 6 radian per second. So for HJW omega, we get 1 over 1 plus j omega over omega W omega C, and we integrate, we get 0.707. So for F0, which is 250 kilohertz, and omega 0 is 2 pi, multiply with 250 times with 10 over 3. So omega 0 over omega C, which is 250 over 750, so we get 1 over 3, and put the value, so the final answer is 0.95. For analysis low pass filter, after all calculation and discussion, Low pass filter was designed using a fundamental frequency of 250 kHz and cut-off frequency of 750 kHz. Since the fundamental frequency is significantly lower than the cut-off frequency, the designer passes through the filter with minimal attenuation. Frequency components above the cut-off frequency, particularly higher order harmonics, are progressively attenuated, reducing unwanted high frequency content. As a result, the output waveform becomes smoother in the time domain, with sharp transition and distortion greatly reduced. So both manual calculation and MATLAB simulation confirm that the filter performs as expected and demonstrated effective harmonic suspension and validating the Abora filter design.
Hello, my name is Amshad Shakir bin Azlan. My metric number CA240106. I will explain about manual calculation circuit of low pass filter. So, we need what I get is our FO is 250 kilohertz and our FC is 750 kilohertz. So we assume that C is 50 power factor. so the FC the ma- so the formula is FC equal to 1 over 2 pi RC. So we need to get our R. So R formula is 1 over 2 pi multiply FC and multiply C. So we get 1 equal to 1 divide to 2 pi 750k multiply 50p, and we get 4244.13 ohm. So this is our circuit simulation. So here we have a simple but insightful RC circuit. The signal source representing by this red and blue icon feeds a square wave into a resistor R1, which has a value of ohm is 4.244 ohms. The signal then passed through capacitor rate at 550 microfarad before being observed at the output. On the left, we see the digital oscilloscope displaying the actual waveform. Notice how the square wave input is transformed as it passes through the RC network. You can clearly see the changing and discharging behavior of the capacitor, resulting in a rounded exponential rise and fall. This is classic RC time constant behavior. To control the input, we are using the VSM signal generator. As you can see, we have set it to produce a square wave with an amplitude of 1.00 volt and a frequency of 250 Hz, ideal for observing the capacitor reaction of multiple cycle. So the conclusion is we need to understand how passive component like resistor and capacitor shape signal is foundational. Whether you are designing filter, timing circuit or power supply, in the next section we analyze this waveform quantitatively, calculate time constant, phase shift and voltage drop. So the analysis for the output of the filter by comparing with the simulation, we designed a first-order RC low-pass filter to meet Group 4 specification with a target cut-off frequency 750 kHz. We are using a capacitor of 50 pF. We can calculate the resistor value to be approximately 4.24 kilo ohm and build the circuit in Proteus. In the time domain simulation, we apply 250 kHz square wave, which is below the cut-off frequency as expected. The output closely follow the input, but it with slightly rounded edge. This happened because the filter attenuated the high frequency harmonic in the square wave while passing the fundamental frequency. To confirm performance, we ran a AC sweep. The frequency response show a flat passband and a 3 dB drop at around 750 kHz, matching our design goal. Both simulations confirm that circuit work as a proper first-order low-pass validating our component choice and design.
This is the MATLAB code used to analyze a square wave signal using a Fourier series and to study the effect of duty cycle variation. First, we define the main signal parameter, including the fundamental frequency, which is 250 Hz for section 1, group 5, the signal period, and the number of harmony used in the analysis. Next, a different duty cycle of 10%, 20, 30, 70, and 80% and are defined. A loop is used to so that the same analysis can be repeated automatically for each duty cycle. For each case, the foreign series coefficient are calculated. This coefficient determine the strength of each harmonic component in the signal. The time domain signal is reconstructed by summing all harmonic components which show how the waveform shape change with duty cycle. In frequency domain, the magnitude of the Fourier coefficient is plotted to show how the harmonic content is distributed across the frequency. Finally, the result of display a subplot where the left side show the time domain signal and the right side show the frequency domain spectrum. This figure show the effect of varying the duty cycles of square wave signal. The duty cycle used in this analytic are 10, 20, 30, 70, and 80 while keeping the fundamental frequency constant at 250 Hz for group 4. On the left side, we can see the time domain waveform for low duty cycles such as 10 and 20. The signal remaining on for a short time, producing a narrow pulse. As the duty cycle increase, the pulse width become wider and the 70 and 80% the signal stay high for the most period. On the right side, the frequency domain plot show the magnitude of the frequency series coefficient for low duty cycle. The harmonic component are spread over wider frequency range indicate the presence of high frequency component. As the duty cycle increase, the harmonic energy become more concentrated at the lower frequency and the higher frequency component decrease in magnitude. This demonstrates the duty cycle has a significant effect on the harmonic content of the signal, which directly influence how the signal behaves when they pass through a low pass filter.
For task 1, we generated 3 sinusoidal signals with a different frequency using a MATLAB. Each signal was summed individually in time domain, then all signals were summed together. This task helps us to understand how a multiple sinusoidal components combine to form a more complex signals. From the result, we can clearly see that a combined signals and a superposition from all 3 individual signals, which follow the principle of a linear in a signal and system. For task 1, focus on generating and combining a sinusoidal signals in a time domain using a MATLAB. In task 2, we applied a fourth series to reconstruct a square wave signal. We analyzed the signal using a different number of harmonics such as 5, 10, and 20 harmonics. In the time domain, increasing the number of harmonics makes the waveform closer to the ideal square wave, although a small shoot appear at the edge due to the depth of phenomena. For the task 2, the square wave is successfully reconstructed using a further series. As the numbers of harmonic increase, the reconstructed signal becomes closer to an ideal square wave. The frequency spectrum shows the harmonic appearing a multiple of fundamental frequencies. From the tax tree, we studied the effect of different duty circles on the square wave signal, but varying the duty circle, we observed changing in both the time domain waveform and a frequency domain spectrum. A lower duty circle is, spread the signal energy over a wide range of a frequency, while the higher duty circle concentrates more energy in a low harmonics. In task 3, a different duty circles are applied to a square wave. The results show that the change in the duty circle affects the both of waveform shape and harmonic distributions in the frequency domain.
Conclusion part. This project successfully achieved also its objective by applying four series and to analyze the periodic square wave and studying the behavior in both time of the frequency domain. The method of analysis showed a strong agreement with the proto-circuit simulation, confirming the reliability and accuracy of the results. The low-pass filter efficiency at the attended frequency component above the cutoff frequency, while the preserving the fundamental signal component below it. In addition, verifying the duty signal sufficiently influence that harmonic distribution of the signal with a higher duty cycle concentrating energy, low harmonic and lower duty cycle spreading energy across a wide frequency range. Overall, the results of the demonstrated of the practice importance of the low pass filter in the signal processing applications such as noise reducing and the collision